Hello everyone. Today we're going to begin a series of tutorials in which we will consider the basis of neural signaling. And to begin, I'd like to give you just a broad overview of different types of electrical signals that are generated by neurons. I've got two learning objectives for you today. I'd like for you to be able to differentiate the resting membrane potential from the action potential. And I'd like for you to consider the action potential and describe one means for encoding information in the activity of neurons. So let's begin. Well, perhaps the most important thing I'll have to say to you today is that electrical signaling is the fundamental neuronal process that underlies all aspects of brain function. So if we want to understand how the brain does its job of processing information, then we need to know about the basis of electrical signaling. Well, this brings us to neurons and their unique properties. However, we've got a bit of a problem, and that is that neurons are intrinsically poor generators of electricity. That is, they just don't conduct electricity very well, being made of biological materials. However, neurons have evolved really fascinating mechanisms to overcome this limitation. And those mechanisms involve the generation of electrical signals through the flow of ions across the neuronal plasma membrane. So much of what we're going to be discussing in this unit of the course has to do with understanding how ions move across the neuronal plasma membrane. Okay, well, let's begin by considering an experiment. I want you to be the neuroscientist, and I want you to have at your disposal a neuron for experimentation. This can be a neuron grown in culture, perhaps it's a neuron living in an actual brain in an experimental animal model system that we have at our disposal, or perhaps it's a computer simulation that will give us a chance to probe the behavior of an actual neuron based on previous recordings of real neurons. Well, whatever the case, we have a neuron in front of us, and we've got the ability to manipulate this neuron and then to record the electrical behavior that this neuron generates. So we have two microelectrodes. We have a stimulating electrode, which we can use to pass current into the cell, and we can either inject negative current or positive current and affect the electrical behavior of the neuron. Well, we can record that behavior with a second microelectrode. Now, let's begin the experiment by first putting that stimulating electrode in place and then just leaving it alone. We'll come back to that in just a moment. And meanwhile, we'll approach the neuronal plasma membrane with the recording microelectrode. And let's use some graphs and follow the behavior of this experiment as we go in time. So time will be progressing on the x-axis in this direction. So there's time. And on the top, in what's labeled panel B at the top here, we're going to record the current that's passed through our stimulating microelectrode number 1. But we're not using it just yet, so the current is just 0, so we're not doing anything there. So we'll ignore that for the time being. What I want us to focus on is the recording microelectrode. Now we begin to approach that microelectrode and we're recording 0 potential. That means that there is no electrical potential between the tip of the microelectrode and a reference wire because they're both essentially in the same medium. That is the solution that's bathing this neuron. But as soon as we insert this microelectrode into this neuron, we see that there is a sharp fall in the recorded membrane potential, which is to say we are recording a potential between the inside of the cell and the outside, with the inside of the cell being negative relative to the outside. And the magnitude of that negativity, at least in this experiment, is on the order of about minus 65 millivolts. So we call this the resting membrane potential. Now, the resting membrane potential can vary from one neuron to the next based on a variety of parameters. It's usually between about minus 40 and minus 90 millivolts. So it's a small potential, but it's significant, and it is measurable and predictable. So we're going to expand upon those ideas as we go through the next few tutorials. But for now, just note that the inside of the cell is negative relative to the outside in the order of about minus 65 millivolts. Now, we begin to use electrode number 1, and we can stimulate this cell with either positive or negative charge. So let's see what happens. As we pass a little bit of negative current into the cell, we can record some passive responses of that membrane. That is, the membrane becomes even more negative relative to the outside reference electrode when we pass in this negative current. Now, we call that hyperpolarization, which is to say the membrane potential is becoming even more polarized than it is when that neuron is just at rest before we did any experimentation to it. Now, we can also pass positive current into the cell, and we see a decrease in the amount of polarization. We call that depolarization. So polarization refers to the magnitude of the potential, and if it's greater than rest, we call that hyperpolarization, and if that potential is less than at rest, we call that depolarization. Now, let's provide an even stronger positive current into the cell. And we note that with these steps to higher and higher positive current values that are passed into the cell. And notice what happens. We no longer just see passive responses, but we see something that looks quite different. We call this an active response. And these explosive, sudden depolarizations of the membrane that look like these spikes are called action potentials. In fact, sometimes we call them spikes for short, for the reason that in a typical time base like what we're seeing here, they do in fact look like very sharp spikes. So what we found here is that with some injection of inward current beyond some threshold, there is a sudden explosive depolarizing event that can occur. In fact, the depolarization can even exceed our zero membrane potential level, meaning that for a very brief period of time, the inside of the cell actually becomes more positive than the solutions that are bathing it on the outside. Okay, let's consider a few other aspects of this action potential before we wrap up this brief tutorial. First, note that there's some kind of a threshold. In this experiment, that threshold is around minus 50 millivolts. If we inject a positive current that depolarizes this membrane beyond about minus 50 millivolts, then we trigger the generation of an action potential. So minus 50 millivolts is what we'll call our threshold, and this generation of an action potential beyond threshold is indicative of the all or none nature of the action potential. And we say this because it either occurs or it doesn't. And if it occurs, we see it at full amplitude. Now notice what happens as we go from a current step that elicits an action potential to an even stronger current step. One might have imagined that perhaps you'd get a bigger and bigger action potential, but that's not what happens. What we see is an increase in the number of action potentials. And this is a very important point. Essentially what we have here is a stimulus that's getting stronger and stronger and stronger. And the way that stimulus strength is encoded by the activity of this neuron is by generating more and more action potentials. So at least at first approximation in this simple experiment, the numbers of action potentials is in some sense proportional to the strength of the stimulus. And this begins to give us some insight as to how information might be encoded in the nervous system. A rapid barrage of action potentials could mean the presence of a stronger stimulus compared to a briefer train of action potentials with fewer individual events. Okay, so this is just a picture of what we might see when we record the electrical activity of a neuron, action potentials can be generated. Action potentials can propagate along an axon that is going to grow out from a neuron like this, so we can imagine there being a series of action potentials being propagated that eventually might come to the terminal where we find a synaptic junction. And there, through a set of processes that we'll describe in a later tutorial, a chemical neurotransmitter might be released that might have an effect on the neurons that are connected with this one particular neuron in question. And so that gets us into the whole topic of synaptic transmission, and we'll have a great time talking about that. All right, well, let's conclude this tutorial by considering what are the mechanisms that make all of this possible. We have to explain the resting membrane potential. We have to explain concepts like threshold, and why is the action potential an all or none event? So in order to explain these phenomena, we need to consider two basic molecular mechanisms that account for neural signaling. And they are the establishment of a concentration gradient of a permeant ion, and then the flow of that ion down its concentration gradient through some kind of mechanism that allows for permeability through the plasma membrane. So these two mechanisms map roughly onto two different kinds of proteins that are found in the neuronal plasma membrane. On the left-hand side of this figure, we see the mechanism for generating ion gradients. And these gradients are formed by active transporters that bind ions and transport them upstream, if you will, against their concentration gradient. So I've got this large arrow here to the left indicating that we're transporting ions from one side of the membrane to the other, building up a concentration gradient. Well, that concentration gradient is a means of storing energy that can then be dissipated if that gradient is allowed to discharge. And that gets us to the second mechanism that we have illustrated here in this slide. And that is the presence of ion channels that allow ions to diffuse through an aqueous pore created in the center of that channel that allows for the passage of an ion across the plasma membrane. Now recall that ions are charged molecules, so they are not going to pass through a lipid bilayer very easily. There needs to be some kind of aqueous pore created that allows that ion to flow, and that's exactly what the ion channel does. So ion channels provide a means for dissipating the gradients that are stored by the action of ion pumps. So we've got two mechanisms here. We've got ion pumps and ion channels. The pumps establish concentration gradients. The channels explain the selective permeability of the neuronal plasma membrane to particular ions. So let me leave you with one concluding thought, and that is that ion pumps establish the concentration gradients that provide the driving force for the diffusion of ions across the neuronal plasma membrane. And in this way, pumps set the stage for the movement of ions through those channels that generate the electrical signals. Okay, this wraps up today's tutorial. We will break down these various mechanisms over the next several sessions. We'll talk in more depth and in more quantitative terms about the basis of the resting membrane potential as well as the action potential. And then eventually we'll move into mechanisms of synaptic transmission, neurotransmitters and their receptors, and then the means by which synaptic strength can be changed through experience. And this is the fascinating topic of synaptic plasticity. So that's where we're going in Unit 1. Thanks for beginning the journey with me, and I look forward to having you with me next time. Welcome to this tutorial on the ionic basis of the resting membrane potential. This tutorial will relate to one of the core concepts in the field of neuroscience. It's core concept number 2, as defined by the Society for Neuroscience. I would encourage you to visit brainfacts.org and navigate to core concepts to learn more about what these concepts are all about. But for our purposes, it's useful to just highlight how this tutorial right now relates to the broader field of neuroscience. And it does so because we're going to begin a discussion about how neurons communicate using electrical and chemical signals. And the concept for today's tutorial, the resting membrane potential, really sets the stage for all manner of communication among neurons. So we do have some learning objectives for you today. I want you to be able to describe the concept of electrochemical equilibrium and relate this concept to the resting membrane potential of neurons. I want you to be able to explain why the permeability of the neuronal plasma membrane at rest to potassium ions and the concentration gradient of this ion across the neuronal plasma membrane together account for the resting membrane potential of neurons. I want you to do so in a rather formal way. I want to introduce to you something called the Nernst equation and challenge you to use the Nernst equation to predict the resting membrane potential of neurons, given knowledge of the concentration gradients of permeant ions. Okay, well, let's begin. Okay, well, to begin with, let's consider two important mechanisms that support all manner of electrical signaling that we find in nerve cells. These mechanisms are supported by two very different kinds of proteins that we find in the membranes of neurons. One type of protein is an ion pump, or an ion transporter. It's illustrated on the left-hand side of this slide. What these pumps and transporters do is translocate ions from a region of low concentration to a region of high concentration, which is why I've drawn this large arrow over to the left, indicating an active mechanism that's pumping ions upstream, if you will, that is, against a concentration gradient. And in this particular example, as this molecule binds an ion from a region of low concentration inside the cell and delivers it across the membrane to a region of high concentration, there's the consumption of energy. And so for that reason, we consider this to be an example of active transport. Now, on the right side of this slide, we have an illustration of the second kind of mechanism that's critical for neural signaling. Once we establish concentration gradients of ions, we can discharge those gradients to create electrical signals. But that requires some means of regulating the permeability of the neuronal plasma membrane to a permeant ion. And this is accomplished via the function of ion channels. So these are integral membrane proteins that create an aqueous pore for the passage of an ion from a region of high concentration to low concentration. So what we see on the right is a means for allowing for ions to diffuse down their chemical concentration gradients. So I want you to see how these two mechanisms work hand in hand. Pumps establish the concentration gradients that provide the driving force for the diffusion of ions across the neuronal plasma membrane. Now, in order to understand how all this works and the significance of ions passing across a permeable membrane, let's begin by considering a simple model system. So in this case, what we have is a semi-permeable membrane that divides some kind of container into two kinds of compartments. And that membrane has ion channels in it that allow for the passage of potassium ions. So what we've done here is we've simply filled a container with a 1 millimolar potassium chloride solution with this membrane running right down the middle. So under these conditions, potassium ions are free to pass from one side of the membrane to the other, and there is no net flux of potassium. That is, just as much potassium goes to one side as back across the membrane to the other. And as a result, if we were to insert wires into either side of this chamber and then record an electrical potential, we'd see that there's essentially no potential difference. That is, the voltmeter would record a potential of 0. Now imagine what would happen if we replaced the solution on one side of this chamber, let's say on the left side of the chamber, with a 10 millimolar potassium chloride solution, such that on the left side we have 10 times the concentration of potassium as on the right. So if we were to do this kind of an experiment, what we would find is that very quickly we would go from the initial condition to some kind of a equilibrium. And that equilibrium will be established as potassium ions diffuse down their concentration gradient from the left side of the chamber to the right. Now, what will happen? Well, potassium ions will move, and potassium ions carry a positive charge. So as potassium ions diffuse down their concentration gradient, what we will discover is the accumulation of positive charge on the right side of this membrane. That is, the right side of this membrane will become slightly positive relative to the left. And in a complementary fashion, we'll have the accumulation of negative charge on the left-hand side of this membrane in the compartment of higher potassium chloride solution. So the positive charge is conveyed via potassium ion. The negative charge is reflected in the dissociation of chloride ion from the potassium chloride compound. Now, of course, these movements of ions across this membrane happen in just an instant. So this equilibrium is established very quickly. And what will happen at equilibrium is that an electrical potential will become established across that membrane with a predictable magnitude of that potential. In fact, in this case, the potential has a magnitude of 58 millivolts, with compartment number 1 on the left-hand side being 58 millivolts negative to compartment number 2 on the right-hand side. So when we establish electrochemical equilibrium, we have achieved a state at which the flux of potassium ions from one side of this membrane to the other side is exactly balanced by an opposing membrane potential. This is in fact the definition of equilibrium. So let me repeat myself and try to make this even more clear to you. So as potassium diffuses down its concentration gradient, an electrical force builds up that is exactly equal and opposite to the strength of the chemical gradient. So in conceptual terms, we have a concentration gradient because we chose to put on one side of this membrane a 10-fold more concentrated solution of potassium chloride. But once that was done, potassium diffused across this semi-permeable membrane to the point where an electrical gradient was established that's equal and opposite in magnitude. And that gradient, as measured by our voltmeter, is precisely minus 58 millivolts. And I want you to understand intuitively, not so much quantitatively, but intuitively, what that magnitude of an electrical potential actually is, and how to get a feel for understanding changes in that potential across a neuronal membrane if you know something about the permeant ions and their concentrations. But before we get to a more formal and quantitative approach to understanding this membrane potential at equilibrium, let's just emphasize again the key factors that are responsible for setting up this potential in the first place. The key factors that are needed for the generation of this bioelectrical potential are a mechanism for establishing the concentration gradient, and that happens via the activity of ion pumps and ion transporters, as illustrated on the left-hand side of the figure. Now, we establish the concentration gradient, but there will be no membrane potential unless there's the passage of ions through some permeability channel. And that's where the integral membrane protein that creates an ion channel comes in. So the ion channel allows for this membrane to be selectively permeable to a particular ionic species. Now, for real neurons in real nervous systems, both of these mechanisms are in operation with respect to potassium ions. In fact, at first approximation, the movement of potassium ions across a semi-permeable membrane is sufficient to explain the resting membrane potential of neurons. Now, I'd like to make just a couple of other points as we pass through this discussion of resting membrane potential. One is that we don't actually have to move a large number of potassium ions in order to establish this potential. So it happens very quickly, and it happens with the movement of a relatively small number of ions. And as a consequence, we really aren't fundamentally changing the concentration of solutions on one side of that membrane or another. So we still have a 10 millimolar solution on one side, a 1 millimolar solution on the other in our model system. Another consequence is that because we have chloride ion on either side of our membrane, and that chloride ion has no channel in this model system anyway that will allow it to permeate, we can establish overall electrical neutrality. That is to say that while there is a separation of charge on either side of the membrane, the solutions themselves on one side or the other are electrically neutral. The positive charge is balanced out by negative charge. And then lastly, I would say that the separation of charge is really only limited to this membrane. Sometimes I like to think about being inside of a cell, and maybe the walls of this room being the plasma membrane surrounding this wall, and if there's overall electrical neutrality, I can move through this space and not feel an electrical charge. But if I were to touch the wall, such as what I might do, if I were to touch the wall, maybe I would get a bit of a shock, because the separation of charge is limited just to that space. Well, I'm not sure how well that worked for you on camera, but I think you get the idea. So the separation of charge is limited just to the perimetry of that cell, that is, to either side of the neuronal plasma membrane. Now, from time to time, I'm going to point you to what I think are some pretty helpful animations that are at the website that supports the textbook that I'm recommending that you read as we work through these tutorials in medical neuroscience. So if you follow the link in the handout that I gave you, or if you navigate to the website from Sinauer Associates that supports Neuroscience 5th edition, you'll get to a series of animations. And I would direct your attention to the animation in Chapter 2 called the resting membrane potential. So if you simply click the link in the PDF file, that should take you right there. Otherwise, you can navigate there on your own. And hopefully, you'll find this animation a useful summary of what we've discussed so far, and even more. Okay, now I think we're ready to consider in more formal, even mathematical terms, how can we predict the equilibrium potential if we know a permeant ion and its concentration gradient? Well, the good news is that this has been worked out, and there's a formulation that explains the relationship called the Nernst equation. Now, I don't want you to have to be burdened with the physical chemistry of all of this. I would rather have you get an intuitive feel for what this equation can do, because I think it's a powerful equation in neurophysiology, and we will refer to it from time to time as medical neuroscience progresses, even when we discuss some clinical implications of this phenomenon. So the Nernst equation allows us to predict an equilibrium potential for any permeant ion, and we will indicate that potential with this shorthand called E sub x, x being any permeant ion. Now, the more formal version of this Nernst equation includes a number of factors. It includes the gas constant, a measurement of absolute temperature in degrees Kelvin, knowledge of the valence of the permeant ion, that is the electrical charge on that ion, a factor reflecting Faraday's constant, which is the amount of electrical charge in a mole of a univalent ion that might permeate a membrane. And of course, we need to know the concentration gradient of the permeant ion, which is a function of the concentration of ion X outside of the cell and a concentration of ion X inside of the cell. Now, as I said, I don't intend to burden you with all of this formality. Rather, what I want to be able to do for you is to give you an intuitive feel for how this Nernst equation can be a powerful tool in understanding electrical signaling in neurons. Now, thankfully, our Nernst equation can reduce down in fairly simple terms if we make a few assumptions. One assumption that we like to make has to do with the temperature in which we're recording, and we can either choose body temperature or room temperature, depending if we're thinking about neurons in our own head or perhaps in an experimental preparation that we might have on a laboratory countertop. We can also make some assumptions that reflect the impact of the Faraday constant, for example, the gas constant, basically parameters that define the world in which we operate. Well, if we were to do all that, we can express the Nernst equation in fairly simple terms. We can say that the equilibrium potential for any given ion is equal to the number 58 divided by the valence term of that ion times the log base 10 of the concentration gradient. That is, the concentration of the ion outside of the cell divided by the concentration of the ion inside of the cell. So this is the form of the Nernst equation that I do want you to know, and it's provided for you in your tutorial notes, your handout for this session. And as I've been suggesting, what I really think is important is that you gain an intuitive feel for what this means. So, for example, just looking at this formulation, this means that the equilibrium potential for an ion is going to be proportional to the concentration gradient. And that proportionality is going to be influenced by the valence of the permeant ion. Now, let's start in a very simple situation. Imagine we're dealing with an ion like potassium. So the valence term is actually 1. So now we can just imagine that the equilibrium potential for potassium is going to be 58 times the log base 10 of the concentration gradient. And to keep the math simple, for every 10-fold change in concentration gradient, we can expect a equilibrium potential of 58 millivolts, with the sign of that potential having to do with whether the concentration gradient favors the inside or the outside of the cell. Now, I'd like to pause for just a moment and give you some study questions to consider. These study questions are printed for you at the bottom of your tutorial, so you can look there, and I would encourage you to respond to the questions online now as you work through this tutorial. Okay, well, working through those problems hopefully gives you some feel for what would be the impact of a change in the concentration gradient of a permeant ion on the membrane potential of a neuron. Now, as you have surmised, I'm sure, we've been dealing with a fairly simple situation where we've had a membrane that allows for the passage of just one ion, and we've only really considered one kind of permeant ion. And of course, the solutions that are found around neurons and within the cytoplasm of neurons has multiple ions, and membranes on real neurons potentially can allow for the permeation of a large number of different ions. So it's useful to have some formulation that allows us to understand the equilibrium potential at any given moment in time if we know something about what ions can permeate the neuronal membrane and then something about their concentration gradients. Well, there's one more equation to introduce to you that allows us to do just that. That is to predict the equilibrium potential when multiple ions may permeate the neuronal plasma membrane. This equation is called the Goldman equation. And the Goldman equation really is an expansion of the Nernst equation that considers the situation when there are multiple permeant ions. So what we have in the Goldman equation are terms that allow us to count for the permeability of ions. That's what these P terms are. And we have concentration gradients with outside over in for potassium, for sodium, and then inside over out for chloride. Now you may be wondering why is the ratio of chloride inside to out reversed compared to what we see here for potassium and sodium. So in order to keep the math as simple as possible, we simply flip the sign of the ratio for chloride, knowing that chloride is a ion with a valence of -1, whereas potassium and sodium are monovalent cations with a valence of +1. So to keep the math simple, to keep the logarithmic functions aligned, we simply flip the ratio for chloride ions with inside over outside. Okay, well, with that said, we can use the Goldman equation to predict at any moment in time what is the membrane potential of a neuron that might vary in its permeability for any one of these three ions. And of course, this equation can be expanded to account for as many permeant ions as we like. Now, let's consider the same kind of model system, but now let's make it just a little bit more realistic by adding to the solutions on either side of the permeant membrane sodium chloride. So, what we have now in our model system is on the inside, or the left-hand side, we have high potassium chloride, low sodium chloride. And then on the outside of this membrane, we have the reverse. We have low potassium chloride and high sodium chloride. And again, to simplify the mathematics, if we want to go there, we're going to stipulate that the concentration gradients are tenfold from one side to the other for each ion. Now let's consider what we have in the resting state of a neuron. In the resting state, the permeability of the membrane for potassium is very slight. There's a little bit of movement of potassium from one side of the cell to the other, specifically from the inside to the outside, but not much. Just enough to allow us to establish a resting membrane potential. So essentially, the permeability of the membrane at rest for potassium is so much larger than the permeability for sodium that we can completely ignore that contribution. And what we find is that the resting membrane potential is very close to the Nernst equilibrium potential for potassium. Not quite, because real membranes are a bit more complicated, but in principle, the resting membrane is explained by first approximation to the Nernst prediction for a membrane that's permeable for potassium. Now, imagine there's some mechanism in the neuronal membrane that can flip these permeabilities, such that the permeability to sodium is so much greater than the permeability to potassium that essentially this situation dominates, where now sodium is so much greater than potassium, sodium's the only permeant ion we need to be concerned with. Well, when we do that, we would find that the membrane potential approaches the Nernst equilibrium potential for sodium. And likewise, if we were to flip once again those permeabilities, what we would find is that the membrane potential would fall back down towards its starting point, its resting membrane potential. Well, these considerations, built upon your study with the Nernst equation, gives us an intuitive feel for what's going on with an action potential. The action potential is this explosive electrical event that happens within a neuron, where the membrane potential depolarizes. In fact, it even overshoots zero, such that the inside of the cell becomes very transiently even more positive than the outside. And just as quickly as that depolarization occurs, the action potential seems to fall back down towards rest, although it actually undershoots the resting membrane potential. That is, the inside of the cell becomes even more negative than it typically is at rest, but just by a little bit. And then it decays back to where we started. These considerations of permeability changes for permeant ions, sodium and potassium, provide us with a framework for understanding the ionic basis of the action potential. And that's where we're going to go in our next tutorial. But before we get there, let's just return to the Goldman equation and emphasize some of these considerations. Now, at the resting state, the Goldman equation essentially reduces to the Nernst equation for potassium. That is, the permeability for potassium is so much greater than the permeability for these other factors that they basically disappear. And what we have then resembles the Nernst equilibrium potential for potassium. And predictably, the membrane potential then approaches that theoretical limit predicted by the Nernst equation for potassium. At the peak of the action potential, the Goldman equation essentially reduces to the Nernst equation for sodium. That is to say, now the permeability for sodium is so much greater than the permeability for potassium that the potassium term essentially disappears. Now, we've not talked much about chloride, and that's because for all practical purposes in this consideration, the permeability for chloride is very close to zero. And what permeability there is, chloride will simply follow the movement of these positively charged ions. So we can essentially take chloride out of the consideration. So again, at the peak of the action potential, the Goldman equation reduces to the Nernst equilibrium potential for sodium, such that the membrane potential approaches this theoretical limit. So as we've worked with the Goldman equation just a bit, I hope that you've been able to develop a bit of an intuitive feel for how changes in membrane permeability can change membrane potential. Now, what we haven't talked about at all yet is how do those changes in membrane permeability come about? Well, perhaps a surprising answer is that changes in membrane permeability are themselves influenced by the change in membrane potential. This is the ionic basis for the action potential, which we'll have more to speak about in the next couple of tutorials. For now, I think I can summarize the main message that I've tried to convey to you in the following statement, that voltage-sensitive changes in sodium and potassium permeability are necessary and sufficient for the production of action potentials. Now, before we talk in more detail in forthcoming tutorials about the ionic basis of the action potential, I think it'd be well worth your time to consider more deeply the nature of electrochemical equilibria. This concept will come up in several more sessions as we continue to talk about the basis of neural signaling and the properties of ion channels. So I would encourage you to view one last animation, also available at the website that supports our textbook. It is animation 2.2, which is all about understanding electrochemical equilibrium. You can find a link for that at the end of our handout for this tutorial. So next time, we'll think more together about the ionic basis of the action potential. Hi everyone, welcome to this tutorial on the ionic basis of the action potential. What we're going to talk about today relates once again to one of our core concepts in the field of neuroscience, and that is that neuroscience communicate using both electrical and chemical signals. So today we're going to talk about one of the most important mechanisms within the nervous system for communicating with electrical signals. We have some learning objectives for you today. I want you to be able to revisit the Goldman and even the Nernst equations and use those equations to gain an even deeper intuition about the membrane potential of neurons, to actually predict that value given knowledge of the concentration gradients of ions and their relative permeabilities across the neuronal plasma membrane. I want you to be able to describe the ionic basis of the action potential in terms of both the voltage and time-dependent changes in ionic permeabilities that occur across the neuronal plasma membrane. I want you to be able to describe the driving force for current flow across the plasma membrane. Driving force will be an important concept that will help you understand the movement of ions through the ion channels that give rise to the action potential, but also through other kinds of ion channels that are gated not by voltage, but by neurotransmitters. So that discussion is coming up in a few tutorials. Now, as you work through these considerations, I want you to relate with careful precision the time course of the changes in sodium and potassium conductance back to changes in the membrane potential during the course of the action potential. And lastly, we'll talk a little bit about what's called the refractory period for the generation of the action potential. So I would want you to be able to characterize and discuss that concept. Okay, well, let's begin by reviewing some of our foundational concepts that we introduced last time. And that is that changes in membrane permeability underlie the neuronal action potential. And in order to understand these changes in membrane permeability, let's consider some of the principles that are laid out in Figure 2.7. Now, recall that during the resting state, there is a little bit of potassium conductance. That is, a little bit of potassium leaks out of the neuron. So the permeability of the neuron at rest for potassium is some small value that's greater than 0. However, the permeability of that resting membrane for sodium is just about nil. So even though the potassium permeability is small, it's still very much greater than the permeability for sodium. So what this means is that in the resting state, the membrane potential is very close to the theoretical limit predicted by the Nernst equilibrium potential for potassium. Now, if we imagine some mechanism that allows for a dramatic increase in the permeability of the membrane for sodium, we may find ourselves in a situation where the permeability for sodium is so much greater than the permeability for potassium that the membrane potential becomes predictable by the Nernst equilibrium potential, or the Nernst equilibrium equation for sodium, such that the membrane potential approaches this theoretical value that we can calculate, the Nernst equilibrium potential for sodium. And this is essentially what happens during the generation of an action potential. The permeability of the membrane goes from being just a little bit leaky for potassium to now being explosively permeable for sodium. And that will explain the rising phase of the action potential. The falling phase, what we find next, is a bit more complicated, but essentially what we can say is that the permeability for sodium returns back towards 0, and meanwhile the membrane restores its resting state where the permeability for potassium is considerably greater than the negligible or the nil permeability for sodium. Okay, now in order to review all of this in yet a different mode of learning, I would encourage you to consider our formal expression for these changes provided by the Goldman equation. And again, I would remind you that the Goldman equation allows us to calculate an equilibrium potential when there may be multiple ions that can permeate through the membrane. So this equation includes a permeability term for each ion that we might be interested in, and it also includes the concentration gradient, which allows us to consider the Goldman equation as an extension of the Nernst equation for permeant ions. Now maybe this more formal approach is less useful to you, that's okay. If that might be you, then I would encourage you to review these basic concepts of electrochemical equilibrium using the animation provided on the website that supports our textbook. So you can click on the link in your tutorial notes or navigate to that website following the link on our website. And select Animation 2.2 on electrochemical equilibrium. And that will put you in a great shape to understand the concepts that we need to consider to explain the ionic basis of the action potential. Well, finally, before we get there, I'll just remind you that what we talked about last time is that changes in membrane permeability can have predictable consequences for the change in membrane potential. Now, what we're going to try to explain beginning in this tutorial is how is it that changes in membrane potential can impact membrane permeability. Now, much of the work that I'm going to tell you about in this tutorial and the next one that follows is based on the seminal work of two really just amazing figures in the history of neuroscience, Alan Hodgkin and Andrew Huxley. They were both scientists working in England during the time of the Second World War. Actually, just before it was when their interests were being piqued by the possibility of recording bioelectrical signals from nervous tissue. And then World War II intervened. And, well, depending upon who you are, what your family background is, and the circumstances of your family's journey to where you are today, you might consider yourself fortunate that that great war ended as it did. At least those of us in the field of neuroscience are very grateful for the success of the Allied forces, because that allowed Hodgkin and Huxley to return in the mid to late 40s to their work understanding the ionic basis of the action potential. This work was recognized by the Nobel Committee in 1963, when together with Sir John Eccles, an Australian scientist, they were awarded the Nobel Prize in Physiology and Medicine. I would encourage you to read about their biographies, including that of Dr. Eccles, at nobelprize.org, where you can also find their Nobel lectures. Well, what Hodgkin and Huxley did as one means of beginning to explore the ionic basis of the action potential was to construct some circuitry that allowed them to do the kinds of experiments that they wanted to conduct. They recognized that in nature, we often have wonderful animal models that allow us to address the questions that we want to ask. In their case, they chose to examine the giant axon that's present in the body of squid, which were readily accessible to these investigators in their location in the world. Now, in order to study the ionic basis of the action potentials, they wanted to measure ionic currents. But there's a bit of a problem, because with the generation of an action potential, there is a change in membrane permeability that will alter the flux of ionic currents in a way that would make it very difficult to control and to measure those ionic currents. They devised a circuit called the voltage clamp. And this voltage clamp circuit is illustrated here from your textbook. I don't intend to burden you with the details of this, but I do want you to know that for those of you that are interested, you can read more about this circuit there. Essentially what this circuit does is it provides us with an opportunity for measuring ionic current without changing the membrane potential. Hence this term voltage clamp. We can essentially clamp the voltage of an excitable neuronal membrane to any potential that we wish, and thereby measure the movement of ions across that membrane as we do these kinds of experiments. So I mention all this to say that we do want to look at a couple of experimental results derived from studies that Hodgkin and Huxley did as a means of understanding the ionic basis of the action potential. So, let's begin. Now, what we have here in figure 3.1 from your book is a representation of the kind of data that were available to Hodgkin and Huxley. With the voltage clamp method, they were able to set the membrane potential of the squid giant axon to any value that they wished. And here in this experiment, what's being done is a hyperpolarization of the axonal membrane by 65 millivolts. So they're going from a resting value of about 65 millivolts down to about 130, and then they're holding the membrane or clamping it at that potential for some period of time. And they are measuring then the current that can be recorded during this experiment. So what's seen is a sharp transient, which is called a capacitive current. This reflects the way charge is redistributed around the membrane, but otherwise nothing significant is happening. So with hyperpolarization, there are no significant effects on net current that's flowing into or out of the axon. Now, when they passed a depolarizing current step into this neuron, or in other terms, when they clamped this neuron at a marked depolarizing level, that is around 0 millivolts, so they imposed this depolarization step, they saw something quite different and quite remarkable. Following a sharp transient current, what they saw was a transient inward current that was followed by a delayed outward current. Now, just a word about convention here. In these experiments, inward currents are those carried by positively charged ions into the cell, and our convention is to denote that as negative, whereas outward currents are currents carried by positively charged ions that are leaving the cell, and this is denoted in positive terms. Now, there are other more complicated scenarios that we'll eventually discuss involving negatively charged ions, but for now we can keep it simple. So inward current means positively charged ions are entering the cell, and outward current means positively charged ions are exiting the cell. Okay, well, what we want to be able to do is to understand the underlying changes in ionic fluxes that are explaining these two kinds of currents that were recorded, a transient inward current and a delayed outward current. And in order to get there, Hodgkin and Huxley were able to use both some theory and also some empirical investigation of the system. So the theory comes in the form of the Nernst equation. So Hodgkin and Huxley knew about the equilibrium potentials for permeant ions, even though they weren't sure what those ions were at the time that they began their experiment. They knew that in principle one could determine or manipulate a ionic species that you think might be permeating the axonal plasma membrane and use the Nernst equation to calculate the impact of that permeable ion given its known concentration gradients. Well, I'll just remind you then that the Nernst equation is a tool that can be used in studies of this sort, and I'll use that equation to remind you of this concept of equilibrium potential. So remember, at equilibrium potential, there is no net movement of current. So in an experiment like this, we would record a current of 0 at electrochemical equilibrium. So again, this is the point where the concentration gradient for a permeant ion is exactly counterbalanced by the electrical gradient that builds up with the movement of that charged ion. Now, knowing these two facts, it's possible to do experiments then where we can manipulate the membrane potential of an axon or of a neuron and allow for a prediction on the movement of that ion. And as should be intuitively obvious to you, I think, if you choose to clamp the membrane potential at the equilibrium potential for a permeant ion, then that ion is no longer going to contribute to the measured current, because by definition, at equilibrium potential, there's no net movement of the ion. Okay, so these are the kinds of considerations that are brought to bear in the following experiment. So now, what is being described in figure 3.2 from the textbook is the results of producing an experiment now where there are incremental changes in the voltage clamp setting in the depolarizing direction. So we're starting off at rest, somewhere around 65 millivolts, and we are now applying a depolarizing current step from rest to different values of depolarization. First approaching 0 millivolts and then even going beyond 0 millivolts, that is making the inside of the cell more positive than the outside of the cell. And what we see is that as we begin to depolarize this membrane from rest, there is indeed a transient inward current followed by a delayed outward current. But notice the magnitude of these currents. With small depolarizations, the currents that are measured are relatively small. With larger depolarizations, like around 0 millivolts, the transient inward current increases in size, as does the delayed outward current. But now look at what happens to the transient inward current as we depolarize to plus 26 millivolts. This transient inward current is getting smaller. But look at the effect on the delayed outward current. It continues to grow in magnitude. Now, we approach plus 52 millivolts in the experimental data. And what we find is, obviously, quite a large growth of the delayed outward current. But notice, the transient inward current seems to have gone away completely. We'll come back to that point in just a moment. But now let's move on. If we depolarize the cell even further, again, we continue to see growth of the delayed outward current in a relatively monotonic fashion as we change membrane potential in the depolarizing direction. But now look at the point in time where we earlier recognized a transient inward current. What we see is a small inflection in the rise of this outward current. In fact, what appears to be happening is that the transient inward current is no longer inward, but outward. And this might explain this small shoulder effect that we see in the development of this outward current. Okay. Well, these considerations allow us to make a couple of points. First of all, we see that this transient inward current appears to be nulled out with membrane potential around 50 millivolts. And then when we go beyond 50 millivolts, or in this result, perhaps precisely 52 millivolts, this inward current reverses. It becomes an outward current. The second observation we make here is that the delayed outward current steadily increases with increasing depolarization. Now we can measure these currents at particular points in time and plot their magnitude as a function of membrane potential. And when we do that, we have data that look something like this, which capture again what we've just described. And that is that with depolarization, the transient inward current grows, but we eventually hit a point of reversal. And that delayed inward current becomes an outward current, with the crossing of 0 millivolts being somewhere around 50 millivolts in membrane potential magnitude. Now the delayed outward current behaves differently. It continues to grow monotonically with increasing membrane potential. Now, these observations together again provide evidence that this transient inward current reverses near 50 millivolts while the delayed outward current increases steadily. Now, knowing something about the ions that are present in seawater and having some sense of what the ionic contributions might be to the cytoplasm within axons, knowing something about the Nernst equation, and then having the ability to manipulate some of these empirical parameters in the experiment allowed Hodgkin and Huxley to identify what are in fact the ions that are carrying these two kinds of currents. What they concluded is that the early current is carried by sodium. Now, the Nernst equilibrium for sodium happens to be very close to plus 52 millivolts in their experimental preparation. That is highly circumstantial evidence supporting this conclusion that the early current is carried by sodium. One way to test that hypothesis would be to change the solution that is bathing the neuron. And if you substitute the solution with one that removes all sodium, the prediction would be that the inward current ought to reverse to become an outward current. Because even though the normal physiological concentrations of sodium are much greater outside the neuron compared to inside, if you artificially remove all sodium from outside the cell, there will be a concentration gradient favoring the efflux, or the outward flux of sodium. And that appears to be what is recorded in this experiment. And then returning back to normal physiological conditions, similar to what we find in seawater, the inward current is once again restored. This conclusion is further supported by experiments using a toxin found in nature, a toxin called tetrodotoxin, found in the pufferfish. And when that toxin is applied to this axon, what we find is that the transient inward current is blocked. All we're left with is a delayed outward current with the application of tetrodotoxin. So that result provides additional empirical evidence supporting the conclusion that the early current is carried by sodium. Now, additional experiments were done using a tetraethylammonium ion, which is now known to block potassium channels. And when that ion channel blocker is applied to this preparation, what we find is that the delayed outward current is removed, and all that we find is the transient inward current. So this is very good evidence supporting the conclusion that the late current is indeed carried by potassium ions. Okay, well, I think we're ready to move on in our consideration of these data, and I want to introduce an additional concept that I think helps us come a little bit closer to the underlying biological mechanisms that explain the ionic basis of the action potential. And this concept that I want us to think about is conductance. Now, we're familiar with Ohm's law from our study of physics, right? And so Ohm's law is V equals IR, or voltage equals current times resistance. Well, this concept of conductance, while it has more of a formal expression, for our purposes, we can represent conductance by the lowercase letter g and simply state that it's comparable to the inverse of resistance. So it's possible then to rewrite Ohm's law in terms of current. And what we can state then is that measured current is proportional to the conductance for that permeant ion times the voltage. Now, this voltage term is interesting. This voltage term provides the driving force for the current that we can record that is passing through a neuronal membrane. But in order for that current to actually flow, not only must there be a driving force, but there also has to be some means by which that ion can pass through the membrane, which is to say there needs to be conductance. So I want you to appreciate, using this version of Ohm's law, that current flow really requires two kinds of functions. There needs to be conductance greater than zero, and there needs to be some voltage that creates a driving force term. And so rather than saying that the voltage needs to be greater than zero, what we need to express is that the voltage must be greater or different from the Nernst equilibrium potential for the permeant ion. Okay, so this allows us now to return to our experimental situation where we changed membrane potential and recorded current, but now we get to introduce this version of Ohm's law that helps us understand the movement of ions in terms of the conductance of the membrane for the permeant ion. So again, what we have here is current, which can be measured experimentally. We know something about the membrane potential of the neuron, and given the concentration gradient of the permeant ion, we know its Nernst equilibrium potential. So the driving force term then becomes the difference between the membrane potential at any point in time and the Nernst equilibrium potential for the permeant ion. So what would happen then if the membrane potential is exactly the Nernst equilibrium potential for the permeant ion? Under that situation, the driving force is equal to 0, and no net current is going to flow. This is one way to establish electrochemical equilibrium for a permeant ion. That is, it's possible with the patch clamp method to set the membrane potential exactly to the Nernst equilibrium potential for the ion in question. Well, this formulation should make it obvious that there is another way in which to have no net current flow for an ion, and that is when conductance is equal to 0. That is, when there's no means by which an ion can cross a membrane. There may be a driving force, but if there's no conductance, then the measured flow of that current is going to be 0. Okay, well, these are some theoretical ways of considering the experimental results obtained by Hodgkin and Huxley, and what's shown now in the lower part of figure 3.3 are the same data, except now the measured ionic current is expressed in terms of the conductance that is associated with the transient current and the delayed outward current. Now having confidence that that transient current is carried by sodium and the delayed current is carried by potassium. So what we can now do is express these current fluxes in terms of conductances for sodium and potassium. So let's look at these one at a time. When we look at the conductance change for sodium with depolarization, what we see is a very sharp and steep rise in sodium conductance that happens with increasing depolarization. So it should be obvious then that the sodium conductance is voltage dependent. But look what's going on here. Even with a sustained depolarization, this conductance that quickly rises well above 0 falls back towards 0, even though we continue to clamp the axon membrane to some value, as indicated here in the figure. So this tells us that this conductance is not only voltage dependent, but it's also time dependent. Actually, the same conclusions can be made with respect to the potassium conductance, but in a different way. What we see is with increasing depolarization, there is a growth to this potassium conductance. So like the sodium conductance, there's evidence for voltage dependency. But notice the growth is gradual, and the onset of this conductance is relatively slow compared to the onset of the sodium conductance. So there's an element of time dependency that we see for the potassium conductance. Now, that conductance does not fall back down sharply the way we saw for the sodium conductance. Rather, the time dependency is in the relatively gradual onset of this rise in potassium conductance that we see. So, nevertheless, both conductances are time dependent, but the time dependency seems to suggest that there may be different molecular mechanisms that mediate those time dependencies. Okay, let's return now to the sodium conductance and make an additional point about this rapid fall in sodium conductance that we see after the rapid rise. So we actually have a term for this. We call this inactivation. Now, as we'll see in the next tutorial, inactivation is not exactly the same mechanism as simply closing an ion channel. So we're going to want to understand that point in the next tutorial, but for now I'll just highlight the fact that the sodium conductance inactivates. And what we mean by that is this rapid fall in conductance that follows the rapid rise. Now notice the potassium conductance does not inactivate. So there's no inactivation of the potassium conductance. Now there are certain types of potassium conductances that can be found in certain neurons that do in fact inactivate, much like the sodium conductance, but not this conductance, not in this axonal membrane from which these experiments are derived. Okay, I think we're ready to put all this together now and have a computational model that explains the action potential. So what we have here is a precise alignment of the voltage and time-dependent changes in sodium and potassium conductance relative to the action potential. And I want you to spend a little bit of time thinking about this figure, figure 3.8, and considering the alignment of these conductance changes with what we see in membrane potential. And the conclusion of such a thought process is that the action potential is indeed explained by the voltage and time-dependent changes in the permeability of the neuronal membrane to potassium and to sodium. Now let's look first at the sodium conductance and how it's aligned to the action potential. There is a sharp rise in sodium conductance that occurs in time with the rise in membrane potential during what we call the rising phase of the action potential. In fact, the rising phase is explained by this rapid increase in sodium conductance. Now, we haven't explained yet how that itself got started, but we'll come to that in the next tutorial. For now, I'll simply state that some external stimulus was applied to this experimental situation. Or if we can imagine a real neuron or a real axon in a real brain, some stimulus in the form of incoming electrical signaling activity potentially can depolarize that cell and produce this explosive increase in sodium conductance that explains the rising phase of the action potential. But again, let's notice that the increase in sodium conductance is short-lived. Soon thereafter, there's this falling phase, which we call inactivation of the sodium conductance. And in terms of the membrane potential that can be recorded, this is called the falling phase of the action potential. So we had the rising phase on the upslope, and now the falling phase on the downslope. Now, this sodium channel inactivation, I know I'm getting ahead of myself just a little bit with respect to the tutorial notes, but it does allow us to explain an important phenomenon called the refractory period. So there's a period of time during which it's not possible to generate another action potential, and that's called the absolute refractory period. That's happening during this time of sodium channel inactivation, because in order to generate another action potential, these sodium conductances need to be reset back to zero. So this inactivation has to be removed in order for another action potential to fire. So the period of time during which these sodium channels are progressing through their inactivation state is in fact the period of time that we call the absolute refractory period. All right, so let's now turn to the potassium conductance. The potassium conductance is delayed relative to the onset of the sodium conductance, but it's also sustained for a longer period of time. And this sustained conductance for potassium allows potassium to flow out of the cell, and that means positive charge is leaving the inside of the cell. This delayed outward current, or delayed potassium efflux, contributes now to the falling phase of the action potential. And notice that at the conclusion of the falling phase of the action potential, the membrane potential actually undershoots the resting membrane level by just a small degree. So this is called the undershoot. And it is explained by the ongoing efflux of potassium ions. Now, when we first considered the ionic basis of the action potential in principle, it was sufficient to say that the resting membrane potential is approximated by the Nernst equilibrium potential for potassium. Now we can state that that's not exactly the case. The Nernst equilibrium potential for potassium is actually much closer to the nadir of this undershoot. The actual resting membrane potential, I'll call it V rest, in this case is about minus 65 millivolts. Not quite where the Nernst equilibrium potential for potassium would be, because there are other complications, other ionic fluxes that we haven't taken the time to consider, and that's okay. We can simply state that the resting membrane is not an ideal membrane permeable only to potassium. If it were, then V rest would be precisely EK. But there is a small offset, and that allows us to explain this undershoot. Now, we've been emphasizing the time dependencies of these conductances. I don't want to overlook their voltage dependencies. So as the action potential is in its falling phase and undershoot phase, this membrane is now becoming hyperpolarized relative to rest. And as it does so, the potassium conductance trails back down towards its starting point. So as the membrane is hyperpolarizing, returning towards rest, and then undershooting rest, the potassium conductance is shutting down. Okay, well, these considerations allow us to consider just a couple of other aspects of action potential behavior that are worth noting. We've talked some about this concept of threshold. Now I think we can approach this in a bit more of a formal way. We know that there is something like a threshold. We saw that a couple of tutorials ago, where when exceeded, there is a runaway positive feedback cycle where membrane depolarization leads to increased sodium permeability. So sodium rushes into the cell, and that leads to even further depolarization. This is the rising phase of the action potential. Well, that's accomplished when we stimulate the axon, or when the axon and the neuron receive stimulation from some other source, such that the threshold for generating this positive feedback cycle is exceeded. So we might call that a suprathreshold depolarization. Now we can also move the cell in the depolarizing direction away from rest and not hit the threshold for firing an action potential. That would be what we might call the subthreshold depolarization. So what's the difference? What's the difference between a depolarization that achieves threshold and one that doesn't? Well, the difference is whether that depolarization crosses threshold. And threshold, therefore, can be defined as the membrane potential when the sodium current is exactly equal to the potassium current. That is, it's a tipping point where just as much potassium is able to leave the cell as sodium entering the cell. Now, because the sodium conductance opens so much more quickly than the potassium conductance, depolarizations of a sufficient magnitude are certain to trigger an action potential, because we know that it's possible for so much more sodium to enter the cell than potassium leaving the cell that we're driving this cycle past threshold and generating the rising phase of the action potential. Another way to conceptualize this is to consider the regenerative nature of the action potential. We've been talking about this fast positive cycle where sodium is entering the cell, leading to further depolarization and the opening of even more sodium permeability channels that increase sodium current and further depolarize the membrane until the point at which that conductance begins to inactivate. So this is a picture of exceeding threshold and running this fast positive cycle. But we also have a slower negative cycle. And this is set into motion as the membrane begins to depolarize and the permeability channels for potassium begin to open up more slowly. But as they do, potassium channels are opening, potassium is leaving the cell, and this leads to more of a negative feedback, promoting the repolarization and eventually the undershoot of the membrane potential. Now, it's interesting, is it not, that the negative cycle is slow and the positive cycle is fast? This temporal dependency ensures that the action potential can be an explosive event. That is, the rising phase can happen unimpeded by this more slow negative phase. However, the negative phase eventually does dominate. Yes, the sodium conductance is beginning to inactivate, but the potassium conductance will drive the membrane back to resting levels and even below rest into undershoot. So the slow negative cycle seems to be nature's way of ensuring a rapid signaling event, that is, an action potential of a short duration. Now, there are action potentials in nature that can be longer because other ion channels are involved, but our canonical action potential that we find in axons and in neurons is of this sort: a sharp rising phase followed by a sharp falling phase with an undershoot. Now, this slow negative cycle also allows us to explain the rest of the refractory period. I mentioned that the absolute refractory period is when sodium conductances are in their inactive state, and it's not possible to trigger a second action potential until that inactivation state is removed. However, there is a relative refractory period that will be present as long as we continue to have this slow negative cycle turning away, which is to say the membrane potential is an undershoot. Now, during that time, it is possible to trigger a second action potential because the sodium permeability channels are ready to fire again. However, with undershoot, there is therefore a need for a slightly stronger stimulus that can overcome that undershoot and bring the membrane potential to threshold in order to fire an action potential. That's why this refractory period is said to be relative. Well, together then, this fast positive cycle, this slow negative cycle, allows us to understand the shape and the duration of the action potential, and it also raises some interesting philosophical points, I think. It suggests that there is a limit to the speed of processing in the nervous system, and that limit is defined by the width of the action potential. Of course, that limit is actually an aggregate of the billions of action potentials that are happening all the time in neural circuits and neural systems. But in principle, there is a limit to what can be defined as the moment. In fact, the aggregate consequence of this action potential width is that our brain is perpetually living in the past. We are processing right now information that just happened a few tens or perhaps even hundreds of milliseconds ago. No, I'm not talking about memory. I'm talking about the brain working on the incoming flow of information. And because of the width of the action potential, and as we'll see in a few sessions, the delay that comes with synaptic transmission, it takes some time to elaborate our thoughts and our perceptions and our emotions. So from that standpoint, we would seem to be at something of a disadvantage, living in a world in real time, knowing that our brain is living perhaps a few hundreds of milliseconds in the past. But brains are wonderful organs. One of the best things they can do is predict the future. In fact, our brains are constantly updating our model about the future so that we can anticipate the actions that happen in real time in the world. So even though the width of the action potential imposes a bit of a delay in our neural processing, we make up for that delay by being able to predict behavior in the future. Well, enough of that philosophy for the moment. I think we're ready to wrap this up, and I'll leave you with a study question, which you can find at the bottom of your tutorial, and you can find it online in our next slide. So consider this regenerative nature of the action potential, this fast positive cycle, and the slower negative cycle. And I want you to think about, why is the action potential a spike? That's sometimes the term that neurophysiologists use to describe the action potential. Which of these factors listed below do you think is the best explanation for the short duration of a typical neuronal action potential? Okay, I'll see you with the next tutorial. Hi everyone, welcome to this tutorial on the molecular mechanisms of action potential generation. So in the previous few sessions we've been talking about the ionic basis of action potential generation. Now we want to move more towards the biological question of what are the mechanisms that are responsible for the production of this signature electrical event that we find in excitable tissue. All of this relates to one of our neuroscience core concepts, the one we've been focusing on, the fact that neurons communicate using both electrical and chemical signals. So we continue to talk about the electrical signaling activity of neurons, and very soon we'll be moving in to talk about the chemical signals. Well, for today's session, we have some learning objectives. I want you to be able to describe the molecular properties of sodium and potassium channels and understand and recognize how these properties explain the voltage and time-dependent permeability changes that underlie the generation of action potentials. And secondly, I want you to be able to describe the molecular mechanisms that establish the chemical gradients for these important ions, sodium and potassium, across the neuronal plasma membrane. Well, to begin, let's again reiterate some of our foundational principles. That is, that changes in potassium and sodium permeability underlie the action potential. So we've seen this figure a few times before. It allows us to conceptually understand the resting membrane potential as being a state dominated by the leak conductance for potassium, the rising phase being a phase of action potential generation where there's an explosive increase in the permeability of the membrane for sodium, such that at the peak of the action potential, the membrane potential comes very close to the Nernst equilibrium potential for sodium, because the sodium permeability of the membrane is so much greater than any other ionic permeability. The ability to predict membrane potential becomes, as a first approximation, the Nernst equilibrium equation for sodium. Well, the falling phase of the action potential involves a dramatic reduction of sodium permeability, and this is the inactivation of this sodium conductance. We'll talk about the molecular mechanisms for that inactivation in this tutorial. But in addition, we know that the voltage and time dependency of the potassium conductance means that the potassium permeability is rising at the same time that sodium permeability is collapsing. And those two factors together allow us to return to our resting condition, where once again the permeability of the membrane, due to the fact that there's some leakiness of the membrane to potassium, is greater than sodium permeability. and once again the resting membrane potential is established, being close but not precisely the Nernst equilibrium potential for potassium. Well, this conceptualization allows us to again understand how changes in membrane permeability lead to changes in membrane potential, and as we discussed last time, and we'll talk about the mechanisms today, changes in membrane potential can in turn have an impact on changes in membrane permeability. Now, I would encourage you to view again the animation that's available on the website that supports our textbook. It's animation 2.3 on the action potential. You can click following the hyperlink on your tutorial notes, or just navigate on your own to that website. All right. Well, for today, what we really want to understand is what are the molecular mechanisms that allow a change in membrane potential to impact membrane permeability. And this drives us to consider the actual integral membrane proteins themselves that constitute ion channels for sodium and potassium. We'll do so in two ways. First, we'll consider a functional model for how this feature, a change in membrane potential, leads to a change in membrane permeability. And then we'll consider the actual molecular structure of these proteins and gain some insight as to how this plays out in actual biological terms. So first, a functional model. Now, this is an experiment that should be familiar to you now. What we're doing is using our voltage clamp method to apply a step depolarization that is going to be supra-threshold, that is well above threshold for the generation of action potentials. And rather than showing you the action potential or the voltage and time-dependent changes in conductance, I want to show you our current understanding of what's happening at the level of the integral membrane proteins that constitute permeability channels for sodium and potassium. So let's step through this figure in time, and let's look at what happens at the onset of depolarization. So that would be time 0 when we first depolarize. Now, recall that the inward current is fast. That is, the increase in sodium conductance is quite rapid relative to the increase in potassium conductance. And now we gain some insight as to how that might happen. Almost instantaneously, with the depolarization step, the probability of sodium channels reconfiguring from their closed state to the open state is dramatically increased. In other words, sodium channels open at the onset of depolarization. Now notice what's going on for potassium channels. The probability that a potassium channel will go from a closed state to an open state is less than for the sodium channel with this step in depolarization. If we consider the behavior of a single ion channel, which it's possible now to do, we can understand this behavior in more principal terms. But on the aggregate, what we can say is that the sodium channels respond as a collection of proteins more rapidly with greater probability of opening with the onset of depolarization relative to the potassium channel. This is why the positive feedback phenomenon is so rapid, and why the repolarization phenomenon lags the explosive rising phase of the action potential. Okay, so let's move a little bit further out in time. Now we are a few milliseconds later, and we see that the sodium conductance is beginning to inactivate. Why? Not because the pore of the channel is pinching down, but because there is a particular mechanism at play here on the inner aspect, that is the cytoplasmic surface of the sodium channel. There is a gate that we call the inactivation gate that swings shut as the membrane becomes depolarized. So we'll talk about what exactly that is and why that's happening in just a minute. But for now, I want you to note that inactivation of the sodium channel is due to the fact that there is this particular cytoplasmic feature of the channel protein that swings closed and plugs up the pore of the membrane from the cytoplasmic side, preventing any further influx of sodium channels. And this is why that sodium conductance rises so rapidly and then falls equally rapidly, because of the development of inactivation. Now, at about this time, our potassium channels are opening up more consistently. That is, the probability of channel opening is greater, and more potassium channels are in fact in the open configuration, allowing for potassium to flow out of the neuron, this contributing to repolarization and eventually the undershoot of membrane potential. Now notice the cytoplasmic surface of this potassium channel. There is no inactivation gate, at least on this particular type of potassium channel. So these channels are going to continue to remain in their open configuration, provided that we continue to depolarize this membrane, in this case with the voltage clamp experiment. It's only with the cessation of depolarization, that is, when we step back down near the resting membrane potential, that we induce a change in both kinds of channels. This hyperpolarization is essential to restore the closed state for both of these channels. For the sodium channel, that means that the pore itself is closed and the inactivation gate is open. For the potassium channel, it means that the pore simply has closed off, preventing any further efflux of potassium ions. Now let me again restate the point about the sodium channel, because it is important. Notice that there's a difference between inactivation and closed. In the inactive state, the pore of the channel is open, but the gate has closed on the cytoplasmic surface of the channel. In the closed state, the pore is stopped up, preventing further flow of ion. However, the inactivation gate has been reset and restored. So when the channel for sodium is back to its closed state, we are now outside of the absolute refractory period. It's possible for this channel to open up again. That is, it's possible for this channel to re-enter a cycle that will allow for channel opening and the influx of sodium. So the absolute refractory period of the action potential is defined in terms of the molecular structure of the ion channel itself. When these channels are inactive, they are incapable of passing current. That inactivation is only relieved with hyperpolarization. So this inactivated state is when we have our absolute refractory period. Okay? All right. Well, the relative refractory period then is a time following sufficient hyperpolarization to reset that sodium inactivation gate. But it's a time when these potassium channels may remain open, and we may still be in the undershoot of the action potential, so it will require a stronger stimulus to activate that sodium channel sufficiently to induce that positive feedback circuit that leads to this explosive, regenerative, rising phase of the action potential. Okay, now let's move on from this functional consideration of how sodium and potassium channels work relative to their voltage and time dependencies to consider the actual molecules themselves. Well, these ion channels are very complex, but they do have some features in common, and I want to emphasize their common features and just highlight some of the differences. So let's begin by thinking about the sodium channel. Well, the sodium channel that we've been talking about is really a complicated integral membrane protein that contains multiple motifs in which there are helical segments of the protein that are passing through the membrane. So we can recognize 4 motifs, with each motif being comprised of 6 transmembrane segments. And these motifs fold together in a 3-dimensional shape within the membrane, constituting the voltage-gated ion channel that's selectively permeable for sodium. Now, as this protein establishes its tertiary shape in the membrane, it's configured in such a way to establish a pore for the passage of sodium ions. And the electrical and physical structure of that ion channel pore account for its selectivity for sodium. I'll also highlight these yellow transmembrane segments that we see in each of these motifs. And these contain positively charged amino acid residues that account for the voltage sensitivity of this protein. Now, there are also additional components to this channel. There's something called a beta subunit that aggregates with the main integral membrane protein that forms this channel. So this is the sodium channel. We think there are probably at least 10 sodium channel genes that express the proteins that are essential for building these channels. But those genes can have multiple reading frames, and the product of that gene can be modified in various ways. So there may be different capacities to modify this basic structure in interesting ways that will have an impact on its function. And in some cases, there may be genetic mutations of these genes that will impair the function of these channels. And that's a fascinating story that you can read more about in a box that's found in Chapter 4. Okay, so that's a brief look at the sodium channel. We actually know more currently about the molecular structure of potassium channels. One perhaps surprising fact is that there are a large number of genes that encode potassium channels, and potassium channels can have multiple different forms that have different physiological properties owing to their distinct molecular structure. The ion channels that are constituted from these gene products typically represent the aggregate of multiple subunits. That is, not just one integral membrane protein, but more commonly 4 integral membrane proteins that come together and constitute the voltage-gated potassium channel, or potassium channel that's gated by some other mechanism. There's a large family of these channel genes and a large number of variations on an ion channel that allows the passage of potassium. So far, we've been talking about the kind of voltage-dependent ion channel that's represented over here on the left-hand side of this illustration. This is a channel that is gated by a change in voltage. So it, like the sodium channel, has a voltage sensor. We'll talk more about that in just a moment. But there are other kinds of ion channels that are sensitive to other factors, such as calcium within the cell. And that is attributable to a cytoplasmic portion of this integral membrane protein that can interact with calcium. And there's a large variety of other potassium channels that we won't mention at this point, but together they contribute to the exquisite regulation of excitability and the nature of electrical signals that neurons can generate. Now, let's back away just a little bit from the more detailed look at the molecular structure of the voltage-gated ion channel and consider, again from a more functional perspective, how these various components aggregate together to form a functional ion channel. So this is a model now of a voltage-gated potassium channel. So we imagine that these 4 subunits come together to constitute a channel, and there's something that we'll call a pore loop that forms from the aggregate of these 4 subunits. And these pore loops together establish the ionic selectivity and the size selectivity for the passage of potassium ions. Now, we've already talked some about the voltage sensor that's part of each subunit, and that voltage sensor is illustrated by these wings out to the side of these subunits that carry positively charged amino acid residues. So in the hyperpolarized state, when the inside of the cell is made more negative, these positive charges in these wing-like structures are drawn inward toward that negativity. The conformational change that happens as these subunits pivot allows for a closure of the pore loop regions, and potassium ions are not able to pass outward through this channel with hyperpolarization. Now imagine what will happen if we depolarize the cell, that is, we make the inside of the cell positive, perhaps by the opening of a voltage-gated sodium channel. Now these wings that bear these positive charges are pushed away by electrostatic forces, and that pivots the subunits in a way that now opens up a pore in the center of this channel, and potassium ions are then able to aggregate and pass out of this pore region. So the function of these ion channels is a reflection of their structure, and the voltage dependency and even the time dependency has to do with the structure of these voltage sensors and perhaps the density of charged residues that might contribute to the kinetics of channel opening. Now, as I mentioned, one of the consequences of the genetic encoding for these ion channels is that mutations can occur that have consequences for neurological function and, in some cases, human health. And you can read more about that topic if you're interested in Box D in Chapter 4 of our textbook. So what we've been talking about so far are the molecular structures that constitute ion channels, and this is a way of discharging those gradients that are essential for generating electrical signals. Now, let's turn to the molecular mechanisms that are responsible for establishing those gradients in the first place. I mentioned when we first introduced this topic that those gradients are established by ion pumps and ion transporters. And here we see a variety of pumps and transporters. Probably the most important that I should emphasize is right over here on the left-hand side of figure 4.9. It's the sodium-potassium ATPase. This is arguably the most important molecule in the nervous system. It seems a little ridiculous to even make such a claim, but if it were possible to identify one molecule of supreme importance, this would be it, the sodium-potassium ATPase. It consumes a significant portion of all of the energy that is burnt up in the function of a nervous system. And it's one of the principal reasons why the brain requires such a constant and highly regulated flow of blood to deliver oxygen and glucose, the principal substrates for oxidative metabolism in brain tissue. There are other pumps besides the sodium-potassium ATPase, as we see here. There are pumps for calcium. There are ion exchangers that move sodium and calcium and protons. There are cotransporters that can take advantage of a concentration gradient for one ion to transport another. And we don't need to get into all of this complexity at the present time. Rather, what I want to do is consider in a little bit more detail the function of our principal pump, the sodium-potassium ATPase. Now, the story of how this function works is the result of a lot of empirical research that had been done in various ways. One can imagine, based on our prior consideration of the action potential, that one can study this pump by removing either sodium or potassium from a solution and asking how these manipulations might affect pump activity. One might also gain some insight by depriving that pump of its supply of energy to find out what's happening. So these kinds of experiments were done, and what's shown here in figure 4.10 is an experiment where a tagged sodium molecule was allowed to flux across the plasma membrane due to the activity of this pump. So sodium was loaded up within a cell, and the efflux of sodium, which represents the activity of the pump, is measured over time. So as this experiment unfolds, there is some discharge of sodium ions that can be measured experimentally, and if one removes potassium from the medium outside of the cell, now there's a sudden drop in the activity that's being indicated by the efflux of sodium. So this suggests that there must be some kind of codependency between the influx of potassium ions into the cell and the efflux of sodium. Well, when potassium is restored in the fluids around the cell, now the rate of discharge of sodium is restored. But now a key experiment is imposed upon this model system. The energy that's required to drive this activity is depleted by adding a compound which blocks the synthesis of adenosine triphosphate, which is the main energy currency for active cells. And as this metabolic poison, if you will, is introduced, there is a precipitous decline in the efflux of sodium ions, providing strong evidence for the energy requirement of this transport. When ATP is restored, then there is a somewhat rapid rise again of the efflux of sodium back towards the rate at which this experiment was run. So taking these two phases of the experiment together, we know that there's some kind of codependency between the influx of potassium and the efflux of sodium. And we also know that this process is energy dependent. So these kinds of experiments have led to the following model. There is some kind of integral membrane protein that constitutes a pump for sodium and potassium. And this integral membrane protein has enzymatic activity that can cleave ATP and consume energy in the form of breaking that high energy phosphate bond. So we have good reason to believe that there is a configuration of this protein that allows for the binding of sodium ions to the exposed cytoplasmic domain within the central region of this integral membrane protein. And there seems to be a particular stoichiometry to the transport of sodium and potassium. We think there are likely 3 binding sites for sodium ions that are available in this configuration. And then with the consumption of energy in the form of cleaving this high energy phosphate bond from ATP, there's a conformational change such that this protein appears to flip within the membrane. We don't know exactly how this happens, but it seems to change conformation, allowing these 3 sodium ions now to be discharged on the extracellular face of the membrane. And at the same time, this conformational change has exposed now binding sites for potassium ions. Now, with the binding of these potassium ions, the inorganic phosphate is lost and a conformational change occurs, and we are restored to the starting configuration of this protein. And this allows for these potassium ions now to be discharged and enter the extracellular space. So now this protein is ready to return to its starting position in this schema where sodium ions can aggregate. So with the consumption of a high energy phosphate bond, there is a cycle of this pump that transports 3 sodium ions from inside the cell to outside the cell, while at the same time allowing for 2 potassium ions to travel from outside of the cell to the interior. So as this pump churns and burns energy, we establish a concentration gradient with higher sodium ions outside of the cell compared to inside, and higher potassium concentrations inside the cell compared to outside. All of this requires energy. Now, notice the stoichiometry. There's more positive charge leaving the cell than entering the cell with each turn of the cycle. From this point of view, we say that this pump activity is electrogenic. That is, it has the potential to generate a small current. That current typically is negligible unless we're talking about a very small compartment where the concentrations of ions might actually change during the course of a high-frequency burst of action potentials. Such compartments exist in the smallest of our axons that we find in peripheral nerves. So in such situations, as ionic concentrations might be altered by a burst of action potential activity, pump activity will increase, more positive charge will leave the cell as a result of the pump, and the inside of the cell will hyperpolarize. So that would be the impact of this electrogenic nature of pump activity. Again, it's typically negligible except for the very smallest of axons or the very tightest of compartments where pump activity can have an impact on the resting membrane potential. Well, we can summarize and have an opportunity to review these mechanisms of pump activity by viewing an animation from Chapter 4. You can follow this animation by navigating to the website that supports our textbook or by clicking on the hyperlink that you have available to you at the bottom of your tutorial notes. Well, I hope this has been helpful. Our next tutorial will focus on the means by which electrical signals can propagate along an axon. And we will return to some of these concepts related to the structure of ion channels and pumps when we consider synaptic neurotransmission in forthcoming tutorials. Welcome to this tutorial on the propagation of action potentials. This is the final tutorial in a set in which we've been considering the ionic basis of the resting membrane potential, the action potential, the molecular mechanisms involved in the generation of action potentials, and now we're going to talk about how these signals propagate along the length of an axon. So, welcome to my home. It's a chilly, rainy evening. I suspect you can probably hear the rain falling in the background. So please don't mind that. It may sound a bit staticky, but it's really a lovely sound from where I'm sitting, and I hope you can enjoy that with me this evening. Well, let's begin. Once again, our story today on the propagation of the action potential pertains to our second of our 8 core concepts in the field of neuroscience. That is, that neurons communicate using both electrical and chemical signals. Our learning objectives today are that I want you to be able to describe the ionic basis of the action potential in terms of the voltage and time-dependent changes in ionic permeabilities that occur across the neuronal plasma membrane. Same learning objective you saw with our last tutorial. But now what I want you to do is to apply that knowledge to the concept of propagation of action potentials along a length of axon. And that brings us to our second objective, and that is to consider the benefits of adding myelin to an axonal sheath. So I want you to be able to characterize the advantages of myelin for the conduction of an action potential along an axon. Well, in order to set the stage for what I want to discuss with you today, I'm going to recommend that you pause for just a moment and view animation 2.3 at the website that supports our textbook. This animation will account for you again the ionic basis of the action potential. You can click on the hyperlink that's part of your tutorial notes or navigate yourself to the website that supports our text. Okay, well, I think we're ready to move on. And let's consider for some of the properties again of an axon and some of the limitations that need to be overcome as we consider what it takes to propagate an action potential. Now, you'll recall a point that I made right at the start of the course, and that is that neuronal membranes are inherently poor conductors of electricity. One reason for that, of course, is that these membranes tend to be somewhat leaky. They just don't allow for the conduction of electrical charge very efficiently. And this phenomenon is illustrated with the application of a relatively weak electrical stimulus to a length of an axon. So we might call this a sub-threshold stimulus, one that is not going to depolarize the neuron sufficiently to reach threshold for firing an action potential. So threshold in this particular axon is around minus 50 millivolts, and even right near our stimulating electrode, we record a depolarization of only about 7 or 8 millivolts. So not sufficient to bring this neuron from minus 65 to minus 50. But that's okay. This experiment illustrates the point that all we have to do is travel a relatively short length down this axon, just a few millimeters, and already there's significant decay of the current that's been passed at a particular site. So without the presence of myelin, an axon by itself is just not going to provide sufficient conduction through purely passive means. Now, when we talk about the passive flow of current along an axon, this is essentially what we're talking about. With a sub-threshold depolarization, all we have is passive current flow down this axon. And due to the leakiness of the membrane, especially in the absence of myelin, there's just not much hope of conducting an electrical signal more than a millimeter or so. But thankfully, there are indeed active properties that can facilitate the propagation of an action potential. So now, let's look at a length of axon that is stimulated with a stronger stimulus, such that the local region of the membrane is depolarized sufficiently to achieve threshold for firing an action potential. And then let's watch what happens. Okay, this is a bit of a busy figure from your textbook, figure 3.10, but I think it illustrates quite nicely the basic phenomenon that we want to consider. Let me just set up this figure for you just a little bit. So we have 3 moments in time that are illustrated, time 1, time 2, and time 3. And then we have 3 locations along the length of the axon that are illustrated, point A, point B, and point C. So let's begin at time equals 1 and point A. And so this, in fact, will be the site at which we stimulate this axon by injecting positive current at this local site. Now, if we inject sufficient current to depolarize this membrane beyond threshold, what we will have is an action potential. Okay? And that action potential, as you now know, involves the voltage-dependent opening of sodium and potassium channels. First sodium, very quickly, and that allows for sodium to rush in through these open sodium channels. And that sodium now triggers the passive movement of charge along the length of this axon. So that charge is going to go in both directions away from this site of stimulation. Now let's see what's happening as we move from point A to point B. Positive charge is flowing as indicated by the red shading in the middle of the axon. And as we reach point B, now if there still is sufficient depolarization of this membrane, the next batch of sodium channels are going to open up, sodium is going to rush in, and the wave of depolarization is going to continue in this direction from point A to point B and now from point B to point C. But let's return upstream to point A where we initially stimulated to consider what's happening. Recall that the opening of potassium channels lags behind the opening of sodium channels. So this means that while an action potential has been triggered and depolarization has reached point B, at point A now what we have is the opening of potassium channels and the efflux of potassium ions. This means that the initial site of stimulation is now engaged in the process of repolarization. This, in essence, puts a brake on the back propagation of the action potential, allowing the signal to propagate primarily in the downstream direction from the site of stimulation outward. Okay, so now let's arrive at point C, and as with point B, the depolarization is sufficient to open enough voltage-gated sodium channels that the inward sodium current is greater than any leak of potassium current and any voltage-dependent efflux of potassium. And that means that sodium is going to rush in, that positive cycle is going to be regenerated, and the action potential will continue to propagate. Now, if one is to put a recording electrode at each of these points, what we'd see is that at time 1, at point A, we have an action potential. At point B, at a little later in time, we have an action potential recorded. And further along the axon at point C, and a little later in time, we can likewise record another action potential. Now, while point C is firing its action potential, again, the process of repolarization is taking place upstream at point B. So potassium ions are leaving as the potassium channels open more slowly, and that again puts a bit of a blockade on the backwards propagation of that action potential. So this slower negative feedback loop in essence helps to push the action potential down in a direction that for most axons would be physiological. Now, let me make a point about nomenclature. We talk about the propagation of an action potential or the conduction of the action potential as if something's actually moving. Well, what's moving is charge within the cytoplasm of the axon. But really, what I think you can appreciate is that the action potential is being regenerated at each one of these points, A, B, and C. One additional point to make before we leave Figure 3.10, and that is the importance of passive current flow. The passive current flow that I've been speaking about refers to this movement of charge down the axis cylinder of the axon. And as you know from your studies of the movement of fluids through tubes from physics, that the greater resistance, then the less flow there's going to be down that cylinder. The same is true for the movement of charge. So small diameter axons impose greater resistance to the axial diffusion of ions, or the axial conduction of charge. Larger diameter axons offer less resistance and facilitate the rapid conduction of passive current. This is why small diameter axons will have a slower propagation rate of action potential conduction compared to larger diameter axons. So one way to speed up action potential propagation is to increase the diameter of an axon, and vice versa. Okay, now what about myelin? How does myelin contribute to the propagation of action potentials? Well, I would remind you that myelin is produced in the central nervous system by oligodendrocytes. In peripheral nerves in the body, myelin is made by Schwann cells. But we're focused mainly on the central nervous system in this course, so I'll use as our example for myelin-forming cell the oligodendrocyte. So you'll remember that the oligodendrocyte grows out a plasmalemma, or a layer of membrane, that then wraps around a segment of axon. The length of that segment is typically about 1 millimeter, sometimes more, sometimes less, but typically 1 millimeter. And at the junction of a myelin sheath that's formed by one cell and a different cell is a gap. And that gap is known as a node of Ranvier. And at this gap, we have a concentration of ion channels. Channels for sodium and channels for potassium, allowing for the regeneration of action potentials at the nodes of Ranvier. In between the nodes of Ranvier, we have a tight wrapping of myelin, which serves to increase the passive current flow by making the myelinated segment of axon much less leaky than it would be otherwise. So more charge is effectively transferred from one node to the next. There's another advantage here to the presence of myelin, and that is that this node of Ranvier presents a limited space for the concentration of ion channels. Without myelin, to ensure effective propagation of action potentials, one might imagine a much larger number of ion channels would need to be inserted into the membrane in order to ensure propagation. But with myelin, a smaller number of ion channels can be concentrated in much less surface area along the axonal plasma membrane. So this leads to greater efficiencies as well as greater speed of conduction. So let's look at how this works. Consider a similar kind of an experiment, looking at a length of axon at 3 points in space along the length, but also at 3 moments in time. And consider what happens when a stimulus is applied, let's say, to point A. So when this happens, as we saw previously, voltage-dependent sodium channels open, sodium rushes in, and positive charge now can very effectively and very rapidly passively diffuse down along the length of myelinated axon until the next node of Ranvier is reached. We'll call that point B, and here sodium channels are opened. More sodium can rush in as the action potential is regenerated here. And that positive charge now, again, effectively, passively diffuses down that axon and reaches our third point, point C, again regenerating the action potential as sodium ions rush in. Meanwhile, upstream at each of these sites, there is the delayed opening of potassium channels. So potassium flows out, the membrane repolarizes, again putting the brakes on the back propagation of that action potential. The same would be true, of course, with the repolarization of the membrane at site B, as an action potential is generated one nodal length in the downstream direction at point C. So, the advantages of myelin are really twofold. One is an increase in the propagation of action potentials in terms of both the efficiency and in terms of the conduction velocity. But also there is an advantage of economy. Fewer ion channels need to be produced by the cell body and inserted into a much more reduced surface area of axonal plasma membrane. Now let's compare the generation and propagation of action potentials in an unmyelinated axon that might be sitting in a spinal nerve right next to a myelinated axon. The unmyelinated axon might be a postganglionic axon derived from an autonomic nervous system neuron. The myelinated axon could be a sensory or motor fiber present in peripheral nerve. And if we stimulate nearby locations along that nerve, we might drive sodium into both of these axons and trigger an action potential at the same time in the same place. But because of the presence of myelin, the propagation of positive charge is going to be much more rapid and much more efficient in the myelinated axon compared to the unmyelinated axon. And so we are able to generate the second action potential efficiently at the next node in just a fraction of a second. Meanwhile, in the unmyelinated axon, in order for there to be effective conduction of action potentials, we need to put very many voltage-dependent sodium and potassium channels along the length of this membrane to ensure the regeneration of action potential at each adjacent point along its length. Now, as we continue to move down that axon, we see that, at least in this illustration, we've about doubled the relative conduction velocity of the myelinated axon compared to the unmyelinated axon. Again, with the additional advantage of fewer ion channels are needed only at the nodes to regenerate the action potential, compared to what must be necessary in this unmyelinated axon, where the action potential must be regenerated at each adjacent location in the membrane. Now, there's a term for the type of conduction that we see in a myelinated axon. It's called saltatory conduction, which means to jump. So the implication is that the action potential jumps from one node to the next along the length of this myelinated axon. And it's because the action potential need not be regenerated along each adjacent segment of membrane. Because of the efficiency of the passive flow of current along the length of the myelinated segment, action potentials only need to be regenerated at each node. So there's this jumping of signal from one node to the next, to the next, to the next along a myelinated axon. So I'd like to leave you with a study question that will challenge you to consider how these concepts might play out in a clinical condition that might affect the integrity of myelin sheaths around axons. One of the more common conditions that can produce this result is multiple sclerosis. So consider the study question that you can find here, as well as at the bottom of your tutorial notes, and respond accordingly. Lastly, I would encourage you to view Animation 3.2. You can do that by clicking on the hyperlink in your tutorial notes document, or follow your browser navigator to the website that supports our textbook, and view Animation 3.2, Impulse, Conduction, and Axons. And hopefully that will give you yet a different take on this important concept of the propagation of electrical signals along the length of an axon.